Our next presenter will be Professor Walid Tawfiq. He is the chairman of the Department of Laser Application in Metallurgy, Photochemistry, and Agriculture, the leader of the Laser Spectroscopy and Ultra-Fast Laser Group, the head of the Central Laboratory at the National Institute of Laser, Cairo University. He has many experiences, especially in the field of laser-induced plasma spectroscopy, ultra-fast lasers, and ultra-fast spectroscopy, smart materials applications. He also has collaborated with different international groups in laser spectroscopy and ultra-fast laser at Georgia Technology Chapter University in the United States of America, and also the electrocommunication in Afghanistan. Welcome, Dr. Walid. You are with us, and you can share your screen. Yes, we can see your presentation, and you can begin talking and presenting your work.
Thank you very much. Can you hear me, please?
Yes, we hear you clearly. You can begin your presentation.
Again, can you hear me?
Yes, we hear you clearly. You can begin.
Okay, thank you very much. Thank you very much, Professor Marwa. Thank you, Professor Ahmed. Thank you, Professor Hiba, for this kind of invitation to participate and share a part of our progress in this very amazing conference. Today we are talking about treatment and instant monitoring of heavy elements in industrial wastewater using graphene-based membrane and laser spectroscopy. In this manner, we will talk about sources of water pollution in Egypt, which is well known, and how we will develop BVA, graphene oxide membrane, to absorb heavy elements from wastewater, why we need LIPS technique, how we can use the LIPS to detect heavy elements, and how we can optimize the whole system for full system monitoring and treatment of contaminated water. Then we will speak about future work and how to convert graphene oxide to reduce graphene oxide to enhance adsorption, and final conclusion. I just want to introduce myself. Maybe some of you don't know me about. I'm a professor at National Institute of Physics, National Institute of Laser Enhanced Science, NILS, which installed in 1994, and I am head of main laboratory and department of laser applications in metrology and environmental sciences. We are going to use one of the facilities which already available in our laboratory. Our main laboratory contains many laboratories inside it, like electron microscope laboratory and neodymium mag laser laboratory and BLD pulsed laser deposition laboratory, thin film deposition coating laboratory. Now we are talking about pollution, which one of the main issues important for Egypt now these days, because we want to eliminate water wastes and reuse some kind of water sources, so that we would like to not only treatment water, but also monitor monitor the water purification and quality before and after treatment. Of course, there are many sources and causes for pollution, whatever it is, man-made or natural causes. We are focused in our work about heavy elements, because heavy elements cause a lot of health problems, as you know, like cancer and so on. In the average, the trace elements or heavy elements concentration from 1 part per billion to about 1,000 part per million in the average in Egypt, in very heavy polluted areas. And of course, even 1 ppm is so much for some toxic elements like arsenic or whatever, so that accuracy of detection of heavy elements is very important. Of course, reducing these elements is important as well. In our work, we used graphene. Of course, through these nice 3 days, we already listened to many speakers about graphene and how we synthesize graphene with high efficiency and using graphene as membrane. So that I will just summarize. I will not focus so much, but I will summarize as soon as possible. Of course, in our work, we will work with graphene-based polymers compositions to enhance the ability to absorb pollutants. Yesterday, maybe one of speakers like Professor Mahmoud Bahgat gave us an indication about that graphene and other membranes can block bacteria with good efficiency. This is will enhance our ability to reduce the pollution, of course. Graphene has many parts. How to prepare? It's very simple. Just procedures of mixing the BVA with graphene using routine chemical procedures. We will get graphene oxide BVA. One of the most important things is that, as I said, graphene can work as sieves, so that it can block all molecules larger than 9 angstroms. The most important thing is that graphene oxide has carboxyl groups and hydroxyl groups, which maybe help us to prepare the graphene mixed with BVA. So that the interaction dynamics between graphene oxide and BVA will be through the available bonding, hydrogen bonding, which give us some kind of combination between them like this. And we got perfect layers of graphene oxide and BVA mixed together, which enhance absorption. Of course, if we can look at the XRD pattern, we will see there is kind of shift between pure graphene and graphene BVA. This shift due to change the band structure, and we can calculate and consider the absorption capacity directly using the well-known formula, and for each element, of course. And using our LIPS system, I will see later on what's mean by LIPS, we can detect how much elements available in our site, and how we can remove them. And if it is absorbed on the membrane layers, we can detect them and calculate the concentration, and we can be sure that the water after the filter is almost pure. Of course, the absorption capacity change with pH. We can change the pH to approve absorption of some heavy element ions. Now we can just give us brief. These slides will give us brief idea about what's mean by LIPS. LIPS mean that laser-induced plasma spectroscopy. Plasma is the fourth cyst of matter. We convert everything to plasma, and we diagnostic the spectra of this plasma. From the spectra, we can put a fingerprint for the emissions from this plasma and know the composition of these particles. The idea is that all of these interactions takes just less than 1 second, and it's very quickly, and no kind of vibration, no chemicals, no nothing. Okay, so the advantages of laser spectroscopy to use with filtration is you can monitor your system 24/7 without using any chemicals, and it give you online monitoring about the quality of the filter and the quality of the water after filtration. Our system can work with gas and solid and liquids, and can detect the elemental composition, whatever the structure of the sample. Of course, there is some kind of dynamics, physics about plasma. I will not go through them so much, but I just give you an idea that we use our laser beam to make heating up the sample and make a very tiny small plasma, something like some microns above the sample, or of course, or in the sample if we are using water, for example. And the plasma emission can be analysis, and from the emission we can know the composition of the plasma. There is a theory about how we can break down in gas or the sample itself, that we increase the density, electron density by time, due to many mechanisms, and passing through shockwave generations, and absorption and heating up and melting. If the sample is the solid state, it will be melt, vaporize, and after plasma we collect the emission of the plasma, and the analysis is the emission of the plasma as a fingerprint of the content inside the plasma. We use almost high laser intensity, about 10 to 9 watt per centimeter square, to avoid thermal effects on the sample, and get a high precision in identification of elements and its concentrations. Why we use LIPS in this project? Because LIPS is like usual atomic emission spectroscopy, like ICP-MS, atomic mass spectrometry, and X-ray fluorescence. Many atomic emission spectroscopy can be work in this idea, but the advantages of LIPS is that we don't need any kind of chemicals, of supplementary gases, and the analysis will take just a few seconds. It is real time, no sample preparation, and cheaper than any other analytical techniques. Of course, there are many parameters we have to optimize to get a good result, but it is straightforward routine work. So that once we make a plasma, we get the measure lines for the content of this sample, and we know the concentrations from the intensity of the emission lines. For example, we can know how much gold inside some precious gold, and the ratio between the gold and copper and so on. Yes, now how we use this is the whole system. This is the laser, and we focus our laser on the sample, and we analyze the spectra, and we got the spectral analysis of this sample, and we can know all the history about the sample composition, atomic composition. So that in our project, it will be as a following. If we have water flow, we start with contaminated water, then our BVA graphene oxide membrane, and then we expect that we have clean water. Our idea is to use LIPS system so that we can analysis in the beginning, analysis on the membrane itself, and analysis the output, the clean water, to be sure that 24/7 our system is working perfectly, and we can know how much the ratio between polluted elements concentrations and clean water concentrations. If the concentration of the heavy elements is permissible or not, we can stop the system. And if the concentration of the elements inside or on the BVA graphene oxide membrane, we can change the membrane or make kind of cleaning it out and reuse it if possible, so that the system can be automatically controlled and monitored 24/7. This will give us opportunity to convert wastewater to clean water with high quality and with less using of necessity of chemicals and gases, and it will be durable all the time. I think so. Our future work that we may use reduced graphene oxide instead of graphene oxide. As you know, if we convert graphene oxide to reduced graphene oxide, we will shift some hydroxyl carboxyl groups, and we make some ability to enhance absorption in the reduced graphene oxide. We will do this using laser to make reducing the graphene oxide, and then combine with BVA in the future. We will see how much the enhancement we got. Of course, this is reduced. This is the spectra of the reduced graphene oxide, and this is graphene oxide. And this is the difference in group participations. This is because some carboxyl groups removed, and of course there is ability for the reduced graphene oxide to increase absorption more than graphene oxide. This is what we expect to get in the future. Of course, another task that this system, LIPS system, up till now is not portable. It is a huge system in our laboratory, and we were looking for fund to make it portable system. so that the whole system, including the filters, the graphene oxide BVA filter and the lip system, can be portable to move to water stations for filtration and monitoring how much the pollution we have. In the conclusion, we have establishment of laser spectroscopy technique to monitor water pollution. We developed BVA graphene oxide membrane to absorb heavy elements from wastewater. Of course, we will make kind of evaluation of the impact of water minerals content changes on resources and environment, and to introduce some environmental aspects in industry by developing a sensitive detection system for leakage of contamination in water through industrial wastes. Our main lab at Niles will be responsible for environmental awareness on water pollution and its effect on national economy, and on the importance of clean water assurance. Of course, this is what we dream to, but I hope that we can collaborate with the group here and everywhere to make this dream available in future. Thank you. Thank you for listening.
Thank you. Thank you for your impressive presentation. The second presenter. To see you in our second conference, and I wish to see you again in the third. And now we have plenty of speakers, Dr. Mohamed, Professor Mohamed, the Department of UI and Environmental Engineering at the University of Alberta, Canada. His research focuses on the fundamental of advanced and the innovative treatment approaches for water and wastewater treatment, natural and industrial, such as oil and gas. Professor Gamal has supervised 28 postdoctoral for the 38 PhD students and 63 master's students, 15 research assistants, 6 research, and he has published 260 research journal papers and 94 research conference papers, 396 conference and workshop presentation, 54 technical reports. Welcome, Professor Dr. Mohamed.
Thank you very much. Thank you. Can you guys hear me?
Yes.
Okay. Thank you. Thanks for the introduction. So as you can see, the topic of my presentation today is the application of membrane bioreactors for the treatment of industrial process water. Mainly, it's an oil and gas-based process water, and I'll give you some insights on the operating conditions and membrane fouling, that experience we had during the project. The outline of my presentation will be as follows: overview of the membrane bioreactors, their application in the treatment of oil sands process water. I'll be referring to that water as OSPW throughout my presentation. And the third topic will be the application of MBR to treat OSPW, and I will finally conclude. So regarding the overview of the MBRs, as you can see from that slide, and a lot of you must know that membrane bioreactors, basically it's a hybrid system that combines activated sludge process or technique with the membrane filtration to have both the biological process, which is activated sludge, or even IFAS, integrated fixed sludge system, in the same reactor with the settling or the solid-liquid separation. In our case here, it's a filtration process using the membrane technology. This way, it's more or less a way more compact system to deal with both biological and filtration or solids-liquid separation processes in one tank. And it can also increase the capacity of the treatment system when it comes to biological wastewater treatment. So basically then the biological process, which is in this case activated sludge or IFAS, in my presentation will be activated sludge treatment or process, will convert the pollutants into a sludge or solids basically from that system, and the solids will be separated using the membrane technology or filtration. And then this is basically what the membrane will do here to separate the liquid from the solids, and we end up with a very high quality effluent that could be disposed of or could be reused depending on the reuse applications. Regarding the advantages of the membrane bioreactor systems, as I just mentioned, they have small footprint or size. They can produce a very high quality effluent or treated wastewater. Can meet strict discharge limits if you want to discharge the treated effluent. When it comes to the BOD or biochemical oxygen demand, total suspended solids, nitrogen, phosphorus, among many other constituents. It can produce very high biomass with a very high biomass retention, which means basically it will lead to a much higher level of treatment, and that will lead definitely with the retention time being on the higher side to have low sludge production. So that will be way less sludge produced from this treatment compared to conventional biological treatment systems with conventional solids liquid separation such as secondary clarifiers. And these systems, due to the high biomass retention, will end up with long solids retention time, which is a good thing for the biological treatment processes. And this is suitable for water reuse or direct discharge, depending on the reuse type and the standards or guidelines that are controlling the reuse applications. And finally, increase stability against changes in influent characteristics, which means any sudden changes in the quality of the influent wastewater, it cannot lead to any significant impact on the treatment system. So it can have this membrane bioreactor system has a very good capacity of absorbing the shock changes in the water quality or the wastewater quality that's entering the system. Regarding the disadvantages, of course, anybody will think of any disadvantages. The first thing will come to mind is the membrane fouling. And the main factors affecting the membrane fouling would be the membrane material. So are you using hollow fiber membranes versus ceramic membranes, biomass properties, feed water quality, operating conditions. All these factors will affect the type of fouling, how fast the fouling can be generated, and how can this fouling be reversed or dealt with. And other disadvantages include high capital and operating costs because of the membrane material. To change the membrane, to start, the capital cost will be high compared to conventional treatment systems, but also not only the capital cost, the operating and maintenance costs pertaining to these systems. And of course, as everybody know, high energy requirements for such systems. Regarding the membrane bioreactor applications, most of the large-scale membrane bioreactors are established for municipal wastewater treatment or surface water treatment. There is a growing interest and need for using these systems for basically industrial applications. And as you can see from that figure, if you look at basically Middle East and Africa, as you can see with time, there is a growing need, not as large as other continents, but there is definitely a growing interest and need for using them. So I will be talking now with the oil sands process water applications. So for those who don't know what oil sands are, this is a map of Alberta. This is a western province in Canada, just east of British Columbia. And regarding the oil sands, what it is that in Alberta, this is one of the largest oil reserves in the world. Over 100 billion barrels are recoverable. And with today's technology, we can recover, a lot of this volume, but also with predicted volume of about 2.5 trillions of barrels in total going to the future. Oil sands production is expected to reach about 4.25 million barrels per day by 2035. So it's a major source of oil. The only difference in this is not conventional oil resource. It's basically oil that's basically, or hydrocarbon that's in mixture with sand. So as you can see from left to right pictures, in the oil sands, there is a combination of bitumen, about 3 to 18%, with water that's in the range of 2 to 10% in terms of the mass content, 50 to 75% sand, and the rest is in the form of clay. So once we go through the extraction via caustic hot water method, it's a method of extracting or separating the oil from the sand and clay and so on. You end up with the middle picture. As you can see, this is basically you produce bitumen with very high viscosity, about 4.5%, with some sulfur content, vanadium, nickel, nitrogen, and oxygen. Then we follow that up by the upgrading process, where we upgrade that bitumen to synthetic crude oil with low viscosity, low sulfur, low vanadium, nickel, nitrogen, and oxygen. So this is basically gives you an idea about this oil sands and how we separate the oil from the sand and clay. But as we can see from that, we use hot caustic water method to separate, so you end up with a process water or industrial wastewater that we need to treat. The top photo here shows you an aerial photo of some of the lakes or ponds where we keep this raw OSPW or untreated oil sands process water in those ponds. And the bottom pictures show you some of these ponds also, or one example of the ponds with a jar containing this raw or untreated oil sands process water. As you can see from the picture, it's not actually clear water, it's highly colored. And I can explain this by its characteristics. For example, it has high complex mixture of inorganic and organic compounds with pH that's in the range of 8 to 9. It has a very high level of acute and chronically toxic impact on a wide range of organisms, such as bacteria, living organisms in rivers and lakes, all the way to the fish. And the organic fraction consists of different things, including naphthenic acids, humic and fulvic acids, benzene, toluene, and so on, basically BTEX compounds, phenols and polycyclic aromatic hydrocarbons, among many others. The inorganic fraction of this process water consists of suspended solids, including sand, clay, silt, dissolved salts, trace heavy metals, and transition metals. Regarding the challenges and needs for dealing with this oil sands process water, the oil sands industry has gone into operations since the mid-70s, which means we have passed decades without releasing any treated OSPW. So what they do is that they separate the oil from the sand and clay using the hot water extraction process. So you end up with process water. And as you can see from the top picture, the sand and the process water after extraction is recycled back. And you can see it's a slurry, muddy water that's recycled back into the tailing ponds. In those tailing ponds, the liquid or the water is separated at the top as a supernatant with some residual solids and organics and salts. And that supernatant at the top is recycled back for reuse, for extraction. So we keep recycling this water many times, sometimes as many as 80 times for extraction. And once the TDS levels or the chloride levels, among many other things, have reached a high level that can basically interfere with the extraction process in terms of the efficiency, this water is no longer used for the extraction and is stored in tailing ponds, or not tailing ponds in this case, would be recycle water ponds. Recycle is stored for now. So there is a growing need now to treat this OSPW that's unused at the moment for being able to discharge it later into the environment or reuse it. So there is definitely a need for basically treating this water for at least reclamation purposes, if not reuse purposes. So as I mentioned a couple slides ago, some of the organics in this water include naphthenic acids. So what are these naphthenic acids? This is a group of alicyclic and alkyl substituted aliphatic and alicyclic carboxylic acids. And they can have basically different structures. They can have different rings, and these rings could be saturated rings or unsaturated, could be aromatic rings. In general, we characterize the structure of these acids as as you can see on the right side of the slide, with compounds that include carbon or hydrogen or oxygen. Some of them are heteroatomic acids that do not include only carbon, hydrogen, and oxygen. They also include sulfur or nitrogen. And these ones that include sulfur or nitrogen, they tend to be more toxic. And there is a ratio or a number, we call it double bond equivalent or DBE. It's actually equal to the C, or the carbon number, minus the number of hydrogen atoms over 2 plus the number of nitrogen atoms, carbon numbers over 2, and then plus 1. So carbon number minus hydrogen number over 2 plus nitrogen number over 2 plus 1. This is the DBE, or the double bond equivalency, and it's one main characteristic that tells us how this structure is complicated. Okay, and by the way, these naphthenic acids can also exist in other oil and gas wastewater, such as those conventional oil gas resources, such as those in Egypt or other places. In terms of the application of MBR to treat OSPW, the objective is to look at we wanted to look at the feasibility of the anoxic aerobic MBR for OSPW treatment, do optimization of the operating conditions in terms of the effect of inorganic nitrogen or hydraulic retention time on the treatment, the effect of also some pre-treatment, and in particular in this study, we looked at ozone as an advanced oxidation process as a pre-treatment step before the membrane bioreactor. And the reason for that is to convert some of the organics into more easy biodegradable organics, so the biological treatment process could be more efficient. And regarding the membrane fouling behavior, we looked at the effect of ozone pre-treatment and the hydraulic retention time on reducing the membrane fouling. We looked at the fouling mechanisms, and we also looked at the microbial community characteristics and how it could be dynamically changed throughout the treatment process. Regarding the OSPW, or the feed water characteristics, this table includes the majority of the water quality we tested for, but in particular, as you can see in this red box, we looked at the classical naphthenic acids, we looked at the oxidized naphthenic acids, and the concentrations were for both were 50 almost and 40 respectively. And when we ozonated the OSPW, we changed the concentration from 50 to about 10 and from 40 to about 3 milligram per liter of these oxidized naphthenic acids. And in this process here, we used ozone dose, or utilized ozone dose of 30 milligrams per liter for reference. This schematic shows you the treatment system we used. We used a raw water tank, and then we used syringe pumps to basically to pump sodium acetic acid or external sources of nitrogen and phosphorus to make sure the biological activity is enhanced at the beginning and acclimated very quickly. And then we followed that by an anoxic tank, where we mix things very well there. And then after the anoxic tank, we pump the water, or the process water, into aerobic tank, where we had aerobic conditions. And in this aerobic tank, the membrane module was immersed in the water. And the membrane here was Medentia membrane. It's a Japanese company that produces ceramic membrane systems. These are micro membranes, and with 1.28 square centimeters, with basically 0.1 micrometer as a nominal opening size, or pore size of the membranes. And following that, we pumped the permeate into a permeate tank, and that's how the system operated. And some of the sludge was wasted from the aerobic tank, and basically that was the schematic of the system. And the MBRs were continuously operated under 6 different operating conditions for about 740 days. Regarding the operating conditions, we have 5 different stages or types of operating conditions. And in order to look at the fouling, how it differed or changed over these operating or 5 operating condition periods. And in the table here, as you can see here, these are the operating periods. And we supplemented nitrogen throughout the treatment with 2 different levels, 25 to 50, or basically 75 and 0, or 50 and 25, and so on. And the HRT was kept constant for the first 3 periods at 48 hours. and then we increased that to 72 hours in the second operating period, and then we dropped that to 12 and then 24. As you can see, we tested different operating conditions and to look at the system performance over this long time of about basically almost 2 years of operation. Regarding ozone pretreatment, we saw a necessity for that to increase the bioavailability of basically the organic compounds that are hardly biodegradable, to make them much easier to biodegrade. And basically, we wanted to decompose naphthenic acids into basically, or the naphthenic acid that has had large number of carbon atoms or large number of carbons and much higher number of rings, or double bond equivalency at a higher level, into a simpler organics that could be easily assimilated by the bacteria or the microorganisms. And this would subsequently increase or accelerates or increase the rate of degradation or biodegradation of the byproducts and the rest of the hydrocarbons and organics in the process water. And basically, to show you some of the results of ozone, from the left-hand side, you can see this is the 2D plot of the naphthenic acids in the raw SPW versus ozonated. As you can see, a lot of the compounds with high carbon number, high Z number, or double bond equivalency got degraded basically into byproducts that are easier to biodegrade. And in that system, because we had alkaline pH, so the predominant oxidizing agent was the hydroxyl radical, or OH dot. And the reason for that is the alkaline pH. And that OH dot, or the hydroxyl radical, as everybody knows, one of the most strongest oxidizing agents out there, and they are non-selectively targeting organic molecules. And regarding the removal efficiency, if you look at in the left side, this is a raw SPW membrane bioreactor. Basically, these are the basically the squares, and then the red circles are the ozonated OSPW MBR, and then the blue triangles, these are the ozone plus membrane bioreactor treatment. As you can see, we almost achieved 100% removal of naphthenic acids at exactly 94%. And basically, that was a very high level of treatment, and that was actually quite a nice surprise to have. Regarding the aerobic degradation of naphthenic acids with different structures or different number of carbons and double bonds or basically rings, as you can see here, it worked really well on all the compounds with different number of rings going, or double bond equivalencies going from Z equal -2 all the way to Z equal -12. But the take-home message here is that for each Z number, or for each Z basically, as the number of carbons increased, the removal efficiency increased, and also as the time of treatment increased, the removal efficiency increased, and which means higher residual naphthenic acid with smaller n, which means this process targets the compounds that are more complex, which is a very good sign. And as the number of carbons increased, this means the hydrophobicity increased, so the absorption onto flux and cake layer increased. So this means we had local abundance of naphthenic acids in the bioreactor to be attacked by the microorganisms that are flocking or accumulating on these flux within the system or on the cake layer. And regarding the carbon number, as the carbon number basically for each carbon number, as the number of Z increased, or the hydrophobicity increased, or the number of rings increased, the removal decreased. And as the time increased, the removal increased. So that means smaller Z means less recalcitrance, more hydrophobicity. So in our process, we wanted to target the less, not the less recalcitrant, but the higher recalcitrance, which is the more difficult compounds to deal with. So regarding the chemical oxygen demand and inorganic nitrogen removal, basically we saw good removal of COD. Ammonia removal was very high, almost 100%. Total nitrogen was quite high as well. And the only thing we have seen is that no substantial removal of OSPW endogenous COD, basically at those levels of 25 milligram of ammonia for 24 hours as HRT, or basically 12 hours or 24 hours HRT. So which means we needed to achieve higher ammonia nitrogen supplement at the beginning to reach a better removal if we wanted to have a good membrane bioreactor process in place. But in general, we had excellent nitrification efficiency throughout the whole duration. Denitrification performance fluctuated as operating conditions change, and this was expected. And this is a picture showing you the different episodes of cleaning that we did, chemical cleaning. And as you can see, the first chemical cleaning only appeared or has taken place only after about 400 days of operation. Before that, we were only doing the physical cleaning or basically washing or periodic washing of the membranes. So we didn't need to do chemical treatment for almost 400 days. And the 3 phases of fouling were conditioning fouling, followed by a long-term slow transmembrane pressure growth and transmembrane pressure jump phase. This is basically for the fouling. As you can see from the picture, the left side picture, the pristine ceramic membranes. The middle one is the low OSPW membrane bioreactor, without any ozonation or ozone pretreatment. The right side showing you the ozonated OSPW MBR treatment, which means ozone had a significant effect on reducing basically the fouling happening on the membranes, and also was much slower scaling happening on the membrane, and also led to much lower TMP growth and also less frequent jumps of the TMP. Regarding the fouling mechanisms, we characterize the fouling mechanism into to be a long-term slow TMP growth due to cake filtration and lower fouling rate in the ozonated OSPW membrane. And so basically the cake filtration or the cake fouling was the predominant mechanism of fouling. And whenever we had transmembrane, basically when we had basically lower fouling rate in the OSP in the membrane because of ozone, but whenever we had TMP jump, that was basically due to complete blocking and higher fouling rate in the ozonated OSPW due to complete blocking. And this is a picture SEM images to show you the different basically fouling that we experienced. And the red means EPS, extracellular polymeric substances. Green means bacterial cells. And this is showing you the SEM of the surface of the membranes. Regarding the major microorganisms in the systems, these were actually the ones shown here in the red block here, or box. And basically we had EPS producers, biofilm facilitators, and filamentous bacteria. To conclude, the anoxic aerobic MBR was effective for OSPW treatment. Both the anoxic and aerobic tanks contribute to the biodegradation of naphthenic acids, among other organics. Within each naphthenic acid class, a large carbon number generally resulted in a better biodegradation. Within each carbon number series or class, naphthenic acids with higher cyclicity or more rings were usually more recalcitrant and harder to degrade. Long HRTs or hydraulic retention times did not guarantee better removal of naphthenic acids. And higher supplemented ammonia nitrogen at the beginning did not improve removal of naphthenic acids. Potential contributors to biodegradation were the bacteria we listed previously. And the low dose ozone pretreatment substantially enhanced the subsequent biodegradation of OSPW. So at 30 milligram per liter of ozone, we can achieve a very good operation of the MBRs of this oil and gas wastewater. And that actually can lead to less bacterial, basically, shock effects on the bacteria. And we have shown improved anti-fouling performance. And this is when we use low ozone dose. And the combination of ozone pretreatment and MBR is a promising candidate for dealing with oil and gas wastewater treatment in the oil and gas industry. Thank you very much for your listening, and sorry to take a longer time. Thank you.
Okay, only one question because we have no time. One question. There is a professor here asking about for the MBR, is the application of ceramic membranes will be less common than polymeric one?
Okay, it's a great question. Actually, ceramic membranes tend to be more expensive than polymeric membranes, but at the beginning. But the advantage of them is that they can, as you can see from that, we never used any chemical cleaning for 400 days. That's unheard of for this kind of process water that has a lot of organics, and also unheard of in dealing with MBRs using hollow fiber or polymeric membranes. So the break-even point for these systems can be longer, but they can last much longer than ceramic than polymeric membranes. So in the long run, they could be worthwhile to use, and their application started to grow. I know that this company provides an MBR system, especially in the Middle East, in Saudi Arabia, and in the Gulf area for oil and gas applications, because of their advantage on the less need to do chemical treatment. And also, even if you do chemical treatment, the impact of the chemical treatment on the material is not as pronounced as polymeric membranes. And their stronger capacity to handle shock loads, and also compared to other membrane systems, especially if you're dealing with actually wastewater that could generate fouling or biofouling that could be quite aggressive, they have higher resistance than typical polymeric membranes, as far as I know. And by the way, I should mention that in my research group, I don't do it in the last couple of years at least, but we used to do a lot of membrane research, not only for membrane bioreactor, for typical membrane applications such as RO, forward osmosis. We also sensitized our own membrane material using nanocomposite materials, with also like infusion with different nanoparticles for self-cleaning and whatnot. So we have done quite a bit of membrane work in the past. Thank you.
Okay, thank you for your illustrated brief answer, Dr. Mohamed. And any other questions will be sent to you later.
Thank you.
You're welcome. Thank you. Now we move to the second speaker, the third speaker in this session. Yes. Our next speaker will be Dr. Engineer Martin Brecker, liquid media in Germany. His research interest is the study of process engineering. His main subjects are chemical and mechanical process engineering and applied research in national and international research projects for iron and steel industry, water recovery from cooling and wastewater systems. He also has many experience in the boiling water surface and disinfection treatment of oil and heavy metal process. You are welcome, Professor Martin, and you can share your screen and begin your presentation, please.
Thank you very much. First, I would like to thank Professor Abdallah for the invitation to your conference. And it's an honor and pleasure for me to give you an overview of over applications of membrane technology in iron and steel industry. And first, I would like to show some information about a BFI, but I will make it short. BFI is Applied Research Institute located in Düsseldorf in Germany. On the left-hand side, you can see our offices, and on the right-hand side, that is the most important area where we have our research and lab technologies for all kind of investigations we can do. So BFI itself, we have about 100 employees. Our focus is applied research. That is our aim at each end of the project. We would like to have a prototype or a partner who will be able to sell or implement its technology at the sites where we have been performing the trials and investigations together. So we are always looking for partners to work together in national or European or international level to develop and find good solutions which can be applied in iron and steel industry. And today and in the last days, I saw a lot of things where we have the same challenges we have to deal with, especially when it comes to water and how to treat water and recover valuable materials. So BFI has 4 big areas we are working on: Industry 4.0, process and optimization, circular economy, and CO2 reduction. And when we are talking about circular economy and process optimization, then we will come to water. And water is a main issue for the steel industry. Without water, no steel production. And what you can see here is the line of water used in iron and steel production. So the main application is for cooling devices, about 75%, 12% for material cooling, and 13% for air cleaning. So if we take a look to the European steel production, we have a freshwater demand about 2,000 million cubic meter of fresh water per year. So the question is where we need all this water. Well, you can see it here right now. We have these processes with very high temperature, with the blast furnace at the beginning, then the electric arc furnace, casting and hot rolling. And there we need water, especially for material cooling, plant cooling, and we have a lot of intake inside the water, like salts, oil, grease, suspended solids, and from gas washing, we have cyanide and similar stuff inside. Then we have further applications where we need water as well. So if we have pickling, that means removing a scale from the metal with acid. We have rinsing bases. We have cold rolling, where we have emulsions, which contain oil up to 10% weight%. And finally, we have the application where we are coating the metal sheets with nickel or zinc, for instance, and we have rinsing water in a high amount. So what you can imagine is that we have a lot of different kinds of water with different compositions, and of course, each application requiring a special solution. So now you can see here some samples taken from industry. So on the top, you can see this is samples from a cooling water circuit just taken to different periods during the production. Now we have oily wastewaters and emulsions. And here are rinsing water with a pickling acid containing fluoride acid. So what we have for membrane technology especially are two application areas. First is to remove suspended solids, oil and grease. That means to remove undissolved components. And the second one is to remove dissolved components, as for instance, nickel or copper, to recover valuable materials, to use them metallurgical or in the process itself again, or just to recover the process solution by removing disturbing ions, for example. So what are the dimensions we are talking about? We have here flow rates in the cooling water devices between 100 to 10,000 cubic meter per hours, in the average 1 to 2,000 cubic meter hours flow rates, degreasing bases with flow rates up to 10, or pickling bases up to 20 cubic meter per hours. And when it comes to waste acid, we have waste flows up to 1 cubic meter per hour, all depending on the size of the site we are talking about. So why we are doing all this? First is to recover the process solutions. We would like to save water, and we would like to recover valuable materials to save money and to use them again. And the final aim overall is to decouple the production process from freshwater demand as far as it is possible. So when it comes to iron and steel industry, I have here a table with some applications. So the classic one is a pre-treatment of the intake water. That means softening, desalting with reverse osmosis. Then the second application it was performed in iron and steel industry is the ultrafiltration for the removal of oil and the suspended solids in degreasing solutions. And this is a challenging area, as well as the treatment of oily water, as we heard today from Professor Shabali. That it is a challenge because every degreasing base, every emulsion is different. And of course, we are looking all to the one unique membrane which can solve all problems, but it's still a challenge. So what we have further on is a recovery of acids. Then that means you have to remove suspended solids at first and disturbing ions. And of course, this is a very big challenge for membrane materials regarding corrosion, regarding chemical stability. So different treatment methods were used and investigated to find out which is best for which application. So it's like nanofiltration, membrane distillation, or diffusion dialysis, and the method Professor Rögner explained today, like the ED we heard about this afternoon. So further, what we can apply is nanofiltration or membrane extraction to recover nickel or zinc. And finally, another application is the wastewater treatment to reduce the sludge amount, to fulfill the discharge limit, and to remove all the metals which are disturbing. So this was performed by dynamic cross-flow filtration with rotating disc. And I would like to say something more about this application. So we have the problem that sometimes we have in discharge, we have waters with metals containing complexing agents, and that means it's with conventional lime precipitation not always possible to fulfill the discharge limits. Further on, we have a very voluminous sludge amount occurring, and it's expensive to dispose in. Up to 400 euros per ton has to be paid. So the idea was to reduce the sludge amount to recover these metals we were losing with the precipitation, like zinc and nickel, and find a good way to realize it. And the idea was to use a rotating ceramic disc like this. This has a diameter about 300 millimeter. We have a pore size about 0.2 micrometers for the precipitation investigations. And we can use a pressure up to 5 bar in this site, this application, and the maximum rotation speed is about 1,000 turns per minute. So the investigation was performed to find out the best conditions to recover zinc, for instance, in this application. So one of the steps was to find a better precipitation agent, and we found an inorganic sulfatic precipitation agent, which has a big advantage that you can achieve much lower residue metals contents inside the water. In fact, 20 times lower than with conventional lime precipitation. And what we further saw is that we can reduce the sludge amount occurring about 56% by using this precipitation agent. So here on the bottom, you can see some samples. This was a feed sample, the permeate, and this was a concentrate. And the concentrate consists of 28% dry substance and finally 10% of zinc, which can be reused in a metallurgical way. So here you can see the influence of the rotation speed. If we operate with maximum speed with 1,000 turns per minute, then you can see we can operate very long compared to the other applications, and we do not have to clean as much as with lower rotation speeds. What we further saw is that the kind of precipitation agent has a very high influence to the flux and the operation time as well. So we investigated this caustic soda, we investigated classical lime, and we investigated this polysulfide. And what we saw is if we use caustic soda and operate it with this rotating disc, we finally produced a kind of soap inside the test plant that we had to stop the investigation at that point because mechanical forces were getting too high. But if you compare it with this fluoride, with this polysulfide, you can see that the operation was going very proper. What we further did is the investigation of rinsing waters. Rinsing waters are always challenging because you have this suspended solids, you have very low pH values, and you have disturbing metals and some valuable metals. And the challenge is to remove these valuable materials from this mixture. So what we did is to investigate an iron-containing diluted oxalic acid with a microfiltration to remove the suspended solids, and the nanofiltration from to recover these valuable materials, and we were successful with that. what we can see here is further all applications and technologies we have with BFI, we have in lab size, but as well, we have it in a mobile plant, test plant site with flow rates between 100 to 1,000 liter per hour, and that we are able to go to the sites, investigate direct at the water streams which are occurring at the production site for 2 or 3 months, because in lab we can just only take a sample. We have just a small moment of production and water composition, but to show its applicability in the site, we have to be there, we have to demonstrate at the site for several months. Another technology we were dealing with is we saw this as a membrane-based capacitive deionization, and we see this application for salt contents of 2 to 3 grams per liter in, for instance, cooling water applications. We see this as an alternative compared to reverse osmosis, depending on the application. If we are talking about high loads of solids, it's not a question asked that reverse osmosis is best you can apply a nanofiltration depending on the application and the water. For lower contents, we see this as a promising technology, and this membrane-based capacitive deionization is based on electrostatic adsorption. And what is happening, you're putting a charge on it. You have here membrane, ion exchange membranes, and the ions were collected during the separation period. And after a certain time, when the module is charged, then the conductivity will be repulsed, and you will release all the ion, and you have a concentrate flow rate, a concentrate stream. So what we saw in the field trials at the steel sites, that we made a comparison with over 3 months, and that the membrane, that the MCDI achieved a 20% lower energy demand. One advantage of the MCDI is that you can adjust the water quality you would like to produce. That means the achieved water quality is depending on the energy amount you are taking inside. And if you say you have a high quality water demand, then you have to put a lot of energy inside. If you have a medium, you can just reduce it. And if it changes, you can adapt it as you like. So what we achieved were recovery rates up to 78% regarding the water. And we were able to remove the chlorides up to 97%, sulfate hardness up to 70%. So to give you an idea about the size of this application, we have here on the right-hand side the pilot plant for 2 cubic meter per hour and the lab size side next to it. Here on this application, you can just see that the requirement was to reduce the water conductivity down to 200 microsiemens, and we achieved this, and the chloride content was reduced from 109 to 31. And here is, we call it maximum desalting, that you put as much energy inside the MCDI to achieve a very pure water. And we achieved a conductivity up to 23 microsiemens per centimeter, and sulfate, chloride, and so on below 11 milligrams. That was close to demineralized water. I know it's not the same, but it's in the range, and everybody has to check, is this water quality I produced enough, or do I need demineralized water in that? So regarding the outlook, we have increasing temporary water scarcity, and it's increasing, and the problem is now realized, which was not seen for many years. And so the need to decouple production from water consumption is increasing, and everybody would like to go close to zero liquid discharge. But of course, it's combined with some challenges, because you are accumulating ions, bacteria, and other components in the water. So we need applications to remove this components concentrated in the water, to reuse the water again. And what we did currently is an investigation tube membranes you can see on the right-hand side, which are bigger diameter, but which are coated inside, and they are similar. They are in principle like reverse osmosis membrane. This is the aim to achieve, and it would be achieved by layer coating. So this is an ongoing work. I sadly can just say this few words to this application. So I would like to thank you for your attention, for your time, and the chance to talk to this audium, and I'm open for your question.
Thank you for your presentation. Thank you. Now we move to the next presenter in our session. Professor Sahar, Professor of Engineering and Engineering Department, National Research Center. She has high experience in the membrane fabrication and applications for nanofiltration, inverse osmosis, forward osmosis, and pure cell. In addition, for the reduction of whole fiber membranes, with the development in the membrane process, preparation, and water treatment applications. She has 3 granted patents and 6 under evaluation in the preparation for different types of flat sheet membranes. She has more than 20 international published articles in the development of membrane process preparation and water treatment applications. Please, you have 15 minutes, Dr. Saad.
Good afternoon. My presentation is the development and optimization of membrane bioreactor for treatment of pharmaceutical industrial wastewater. As we know, industrial wastewater constitute a big problem, where the wastewater releasing from pharmaceutical industrial especially is contain many undesirable constituents. These undesirable constituents may be or certainly make inhibition to activated sludge process which contain biomass. This biomass inhibition by this substance or this undesirable constituent. Pharmaceutical industrial treatment option, there are many treatment options: physical treatment, chemical treatment, biological treatment. The biological treatment, anaerobic and aerobic. And anaerobic system, especially with activated sludge process. There are many problems in activated sludge process, such as biomass reduction due to toxicity of microorganisms, which leading to bulking and foaming and activated sludge inhibition. Membrane bioreactor is a combination of biological treatment and membrane. This membrane is microfiltration and ultrafiltration. As we know, carbon source elimination in the activated sludge process carried out by aerobic treatment. Nitrification also by aerobic treatment. Denitrification occurs by anoxic, then aerobic treatment. Phosphorus removal occurs by anoxic, anaerobic, then aerobic treatment, as referred by Dr. Mohamed. So the analysis, complete analysis of industrial wastewater is mandatory to identify the method or integrated biological treatment system needed for complete removal or optimization needed for biological treatment. In this presentation, we use combined system between activated sludge process and membrane bioreactor. Membrane bioreactor, there are three options for presented in activated sludge process. Final treatment of final effluent, as we see in our presentation, or immersed in activated sludge process, or immersed in aeration tank, or outdoor of aeration tank. الهدف بتاع our goals development and optimization of membrane bioreactor for treatment of pharmaceutical industrial wastewater. In this, to achieve this objective, we studying factors that affecting the efficiency of the membrane bioreactor for treatment of industrial effluent. Investigation in the factor affecting the activated sludge process fertility during the MBR. Activated sludge process is preceded by anoxic or aerobic or anaerobic zone. To enhance the activated sludge process, we must use the acclimatized bacteria or from the source of the industrial sector. In this study, we use many drugs such as cough syrup, vitamin C, and ascoseed. These drugs obtained from seed company, nutrient ammonium nitrate, diammonium hydrogen phosphate, trace elements such as magnesium sulfate, monohydrate, magnesium sulfate heptahydrate, zinc sulfide, and so on. Industrial wastewater were collected from different sites from seed pharmaceutical industrial wastewater. The characterization of this industrial effluent are represented as follows. This is a schematic diagram which is consists of anoxic, anaerobic, aerobic treatment tank, بعدين setting clarifier, وبعد كده treated effluent. دي conventional. This is a conventional activated sludge. Membrane bioreactor is the anoxic aerobic tank, then membrane bioreactor, then membrane outdoor of the tank. The investigative parameter which we studied is concentration of ascoseed or drugs, retention time, food to microorganism ratio with pH. Process batch activated sludge process, concentration ranging between 2,000 milligram per liter, retention time from 2 to 24 hours. Food to microorganism ratio from 0.1 to 0.8. pH is between 6 to 7. Synthetic wastewater or industrial wastewater, investigated parameter can 1,000 0.2522 retention time. Food to microorganism ratio ranged from 0.822, pH from 6 to 7. Method First step is sludge acclimatization, treatment of synthetic industrial wastewater, treatment of pharmaceutical industrial wastewater using batch activated sludge system. The second, using membrane bioreactor. Parallel to this step, we prepared the ultrafiltration spiral wound membrane in the National Research Center by Dr. Heba Abdallah and our research team. Conventional activated results and results. Conventional activated sludge results, effect of time, effect of by investigation, the effect of time on COD removal, the maximum COD removal by using activated sludge process is 20 hours, obtaining 82%, and the remaining concentration from 1,002 decreases to 200. Effect of different concentration, we investigated different concentration from 200 to 1,200 removal percent, maximum removal percent obtained 85 through 22 hours. Remaining concentration is 96. Effect of initial food to microorganism ratio, we obtained the maximum removal efficiency at 0.85 food to microorganism ratio, and the remaining concentration is 120. Effect of the presence of anoxic zone before the aeration tank. To save the time used, we put the anoxic condition to remove, to make denitrification, or put anaerobic before aeration tank to phosphorus removal. This effect we investigated separately. As we see in this presentation or in this slide, we investigate the retention time for 1 hour. The maximum removal efficiency obtained at 0.75 minutes. We obtained 65% from the initial concentration. I'm using the initial concentration 1,000 as expressed in COD 2,340, where pH and pH equals 7. The food to organism ratio, which obtained at this time, is 1.46, obtaining 65% removal efficiency. Retention time used, the effect of retention time for industrial wastewater treatment at initial concentration at 2,340, reduced from 1,000 to about 250 through 20 hours. Using membrane bioreactors, this effluent concentration, which released from activated sludge process can be removed completely using UF3, ultrafiltration membrane number 3, which can able to remove most of the organic and inorganic which releasing from this aeration tank. This membrane is prepared in the center with polyvinyl pyrrolidone at different composition of additive. U1, ultrafiltration 1, ultrafiltration 2, ultrafiltration 3, ultrafiltration 4, and the most efficient is ultrafiltration 3. The separation removal efficiency is up to 100% for most of the occlusion tubes. Permeate flux is 175. Characterization of industrial wastewater use and before and after treatment. We achieve the total dissolved solid reduced from 8,800 to 24 milligram per liter. The COD from 2,433 to 76. BOD was reduced from 800 to 879 to 110. Industrial reuse wastewater after treatment can be used from cooling tower, boiler feed water, irrigation and maintenance of plant ground, and others. Conclusion: biological treatment of pharmaceutical wastewater treatment and synthetic solution can be of the selected drugs as for example, as we see, were carried out using a conventional activated sludge process and enhanced activated sludge process. The 4 UF membrane were prepared and tested in the separation of these medicine from wastewater, and the result obtained is and this membrane can achieve the maximum removal efficiency. The biological treatment results indicated that the performance of pharmaceutical wastewater treatment using activated sludge or without anoxic conditions is enhanced activated sludge, which acclimatized to damage as we see at concentration of 1,000 milligram per liter, where more than 50% removed using was achieved through the lower than 1 hour. Activated sludge filtrability is the most important parameter that affect membrane bioreactor plant operation and performance in the different full-scale membrane bioreactor. The value of sludge volume index was enhanced by the presence of anoxic zone from 120 to 70 milli per gram. This indicates that anoxic conditions improve the sludge stability due to formation of microorganisms that prevent membrane fouling. The prepared UF membrane experimental result indicated that separation percentage of asbestos from water is higher than 95 using membrane bioreactor at different concentration of feed and real pharmaceutical wastewater with the permeate flux of 124 liter per meter مربع ساعة. Thank you.
Thank you, Dr. Sahar, for this investor an illustrated presentation.
And now we, Dr. Sahar Harry, the researcher at National Research Center. The research is interested in biodiesel production from microalgae and integrated system of microalgae production wastewater treatment, valorizing the biomass potentially for biorecycling with the rule of wastewater management in creating a sustainable environment.
My presentation is about membrane technology in microalgae cultivation and wastewater treatment. First, in the beginning, I'd like to recognize microalgae and its relationship with wastewater treatment in brief. What is microalgae? Microalgae are unicellular photosynthetic microorganisms living in freshwater, saline, or wastewater environment. Microalgae produce carbohydrates, proteins, and lipids as a result of photosynthesis. And for that, microalgae have a big potentiality for several industries. Microalgae grow extremely fast and can double their biomass within 24 hours, depending on the environmental conditions and the cultivation time. For example, the phototropic cultivation depends on the radiance and the nutrients availability. And this nutrient is available in plenty in wastewater. So cultivation of microalgae are high concentrated at high concentration integrated with wastewater treatment has received increased attention over the past decade for its industrial potential. This slide represents the potentiality of the microalgae. The microalgae is cultivated in two engineering systems. The closed water bioreactor is the closed system, and the open bioreactor, the open system is the open bones. Sure, it needs carbon dioxide, sunlight, nutrients for the photosynthesis process. And after that, the harvested algae is collected after a hydraulic retention time. The biomass from the harvested algae could be used in aquaculture feed and as a solid fuel. Also, the harvested algae could be processed, and the extracted oil is used in biodiesel production, and the extracted oil also as omega-3 could be used in other pharmaceutical products. Also, the protein is suitable to be mixed with the animal feed, and the carbohydrates are potential for bioethanol production via fermentation. Microalgae is not just potential for all these industries, but also it is potential to treat the wastewater, since it uptake the nutrients from the wastewater. This slide will represent the problem in Egypt in wastewater treatment. The local convenient process of wastewater treatment is based on primary and secondary process. And 44% of the national wastewater is not treated. So we treat about 56% only. And just 8% of this treated water is used in restricted irrigation. The rest disposed to the desert. So the conventional method of disposal is indeed harmful to the groundwater and the environment. So we think about the microalgae to treat wastewater. The microalgae has demonstrated the ability to effectively remove nutrients and some other contaminants from wastewater. And this histogram represents the characteristics of wastewater in several municipal wastewater plants. We have high COD and high BOD content. We have sufficient nitrogen and phosphorus contents also for algal growth. So now researchers are thinking about using microalgae to treat wastewater. And yesterday we had a speech for Dr. Saad represent the open system and how we used the open system for treating wastewater. However, this is an effective method for treating the wastewater via the facultative bond followed by the high rate algal bond. But this process needs or occupy a big land footprint. So it should be constructed in the governorate that has a back desert back, a wide desert back. Or as this photo represented, this photo from New Zealand, it is constructed in forests. So we have a big area to construct this system. However, we need to think about the crowded cities to use microalgae to treat wastewater. We have the closed system, the other system for cultivation. And as you know, these are pipes arranged in columns or arranged in rays or a helical shape or even a cylindrical. And we have here the green panels or the green walls. And in Europe, they began to use the photobioreactor in other shapes in the crowded cities. Here is a building that covered with the green panels. These green panels use the secondary or primary wastewater to grow algae. And the algae is used in winter to give this building heat. They call this building is the Forschung building in Germany. This is located in Hamburg. And another research developed the panels, the green panels of, in this system to have a vision region in the panels, because some people don't like the cloudy vision in their houses. So we can use the photobioreactor in the crowded cities for treating the wastewater. So we think to develop more and more the researchers' enthusiasm to create the membrane photobioreactor. The ongoing development of the wastewater treatment system has seen the recent implementation of the membrane photobioreactor concept, integrating photobioreactors with membrane filtration process. The membrane filtration, membrane photobioreactor technology is an emerging algae-based wastewater treatment system through algal productivity in the range of 4 to 55 milligrams per liter per day, and nutrient removal up to 95% for nitrogen and 99% for phosphorus. However, high organic carbon high organic compounds promote the growth of bacteria that accelerate fouling. Therefore, primary or secondary effluent are preferred to be used in algal cultivation in spite of their low nutrient content. Average of nutrient content for the secondary effluent is 20 milligrams per liter for nitrogen and 1 milligram for phosphorus. The theory of membrane utilization is represented in all the lectures before, but we have here for talking about the microalgae. So we are talking about the solid liquid separation, insert retention, biomass concentration, and dewatering. We have the gas-liquid separation in the gas delivery during the photobioreactor and removal, and the solute liquid separation, the feedstock preparation, and effluent recycling. This scheme represents how the photobioreactor. Okay. This scheme represents the photobioreactor and the factors affecting each parameter. The feed by its kinds is controlled by the hydraulic retention time. The aeration is important, in which either it is air that contains carbon dioxide for the photosynthesis process, or the enriched air with the carbon dioxide, or the flue gas, since it is the cheapest source for carbon dioxide. The algal culture in the middle has a solid retention time that controls the biomass productivity, and for sure it is lighted either by the natural lighting of the solar lighting or the artificial lighting like the LED lamps. And the permit is controlled. Sorry, the permit is controlled by the flux, and the cultural cultivation is controlled also by the temperature and pH. All the types of membranes could be used in the membrane photobioreactor, but there are factors affecting the selection of the membrane. These factors are the microalgae species itself, the wastewater characteristics, either it is a primary effluent or a secondary effluent, and the flow rate and hydraulic retention time. They are the three major factors affecting the selection of the membrane photobioreactor. 3 minutes or less. Okay, and now I want to talk about the factors affecting the algal growth. The nitrogen phosphorus factor is very important. That the optimum reported is 20:1. The optimization of radiance increases biomass productivity and therefore the nutrient uptake. The light wavelength that affect the light absorption capacity by microalgae, and the hydraulic retention time, solid retention time, the membrane photobioreactor or membrane technology for algae enables the use of long solid retention time while operating a short hydraulic retention time. The temperature suitable for algae is about from 25 to 30 degrees centigrade. The pH for sure increases by photosynthesis, but exerting carbon dioxide could manipulate this range. Permit flux value on the membrane photobioreactor is directly related to fouling rate. The low flux lower than 2.5% is a good strategy to limit the extent membrane fouling. Aeration is very important to provide it with photosynthesis, also to minimize the fouling for sure will happen. Concentrated carbon dioxide, about 11% volume per volume, is more conductive to biomass productivity compared to the atmospheric air containing 0.04% carbon dioxide. Flue gas is preferred for its cheap price. Increasing the aeration reduce membrane fouling, and the optimum is 2.5 meter cube per meter square hour. The conclusion: cultivation algae in membrane photobioreactor fed with wastewater for treatment purpose is an emerging subject for algal research. Secondary effluent is generally considered for membrane photobioreactor application. The membrane photobioreactor technology is able to achieve algal productivity of 50 to 100 milligrams per liter per day with varying removal efficiency of nitrogen from 30 to 97% and phosphorus from 46 to 93%. That depends on different operating conditions. Generally, effective algal production and nutrient removal efficiency can be achieved under favorable conditions, such as a hydraulic retention time of approximately 1 day, solid retention time of 15 to 25 days, light intensity of around 150 micromole photon per meter square second, aeration with 2% to 15% carbon dioxide, temperature of 25 to 35 degrees centigrade, and pH of 7 to 8. These values may vary for different microalgal species and wastewater characteristics. These are some references for the sources in the text. Thank you, and your questions, please.
Thank you, Dr. Sahar. Now we will move the next presenter, Associate Professor Ashraf Amin, Associate Professor in the National Research Council, and also he has his postdoctoral studies now in the University of Waterloo, Canada. Dr. Amin is specialized in the process design and development in membrane fabrication, optimization using mathematical modeling, renewable energy, and catalysis. Please, Dr. Ashraf, try to take your time, only 15 minutes. We are running away of our schedule. It's a long time.
Okay. So thanks, Dr. Marwa and Dr. Sahar for the kind introduction.
Yeah.
I'm really glad to connect with my colleagues at NRC. It was a long time, and hope everything is going well. So thanks a lot again for giving me the opportunity to present my work at the conference. I'm talking here about an industrial experience that we had with Dr. Salwa Hawash and Dr. Mona Amin. So our team was invited to work with one of the food industrial companies in Egypt, and they have a problem with the effluent. So our team has designed like an effluent treatment unit, and so I'm here talking about a part of this experience, which is developing a mathematical model for treatment of industrial wastewater using activated sludge process in an aeration tank. So I will make sure to finish quickly, as I know we are tight on time. The team has just developed. Sorry, let me maximize. So the team designed activated sludge process for this industrial unit. One of the major problems that we had that the activated sludge process is a dynamic process. So especially in the startup period, until we reach steady state, so there is lots of variables, there's lots of changes that's taking place. So we have designed, or we come up with a solution for this problem to develop a model to study the dynamic behavior of the system and what are the expectations and what are the optimum parameters that can lead to a short startup period, as we will see here through the model. So the proposed model which we have developed is was verified and validated using the industrial data collected from the developed unit. The model including mass balance, heat balance, and different energy equations. The model parameters were fitted, and then we came up with a prediction for the model parameters. We use this to explore or to investigate how the system will behave. And as you can see here, this is present. Here. This is a symbol for the activation, or it's just a presentation of the activated sludge process we have developed. And the model equation, as you can see here, like we have substrate and biomass material balance using these two equations for a completely mixed bioreactor. And also we have like other several equations, but maybe I just presented the most important here. If you need any more information, I would be happy to provide it. The rate of substrate utilization also is calculated using the first equation in this slide. And the maximum rate of substrate utilization is given here. And then we added like more equations to calculate the growth rate and the specific growth rate of microorganisms in the developed unit. So like we have used this model, as I mentioned, like we developed a system for mathematical system for predicting the behavior of the developed unit. We use the industrial information or industrial results we have collected. Also, we have like the team has have done an amazing work at the lab. We used all this to develop the model and to verify the model performance. So far, we have like seen a great agreement between the model performance and the the model expectation and the industrial and lab results. So we use this model to understand more how the system behaves. And there was like two main parameters that need to be studied. The first one is the biomass concentration, and the second one is the substrate concentration. And this is where I will focus on my results section. So first, like as you can see from the graph here, how the biomass concentration changes with time. So we have like varied the biomass concentration in the inlet or the feed for the system from 2 to 4 kilogram per meter cube. And as you can see, like from the graph, there's almost no variation. So we have come to a conclusion that the biomass concentration almost like is a weak factor or doesn't have any effect on the system performance. So we have studied like different biomass concentration. We have studied how this affects COD, BOD, substrate concentration in the effluent. The result indicated that the steady state value is almost the same despite the value of the inlet biomass concentration. And the substrate concentration usually reaches around 0.2 kilogram per meter cube, whatever you start with, and COD and BOD are shown here. So just as a sample also of how the biomass concentration variation affecting the COD. So as you can see here, like COD didn't change so much, even like during the dynamic period, there is slight variation here. And by the end, it reaches almost same value around within 35 to 40 days of operation. And this is where the system reaches steady state. On the other hand, like substrate concentration has really showed a great effect on system performance, as you can see here. So either during dynamic period or at steady state, the substrate concentration showed how much like a great effect on the system performance. And we have varied the substrate concentration between 0.15 to 0.3 kilogram per meter cube. Our results indicate that the substrate concentration is like the major factor affecting the performance of the system. Once you reach steady state, this is totally affected, like the values of the system, the outlet concentration or outlet properties are affected so much by the initial substrate concentration or the inlet substrate concentration. So we have came to a conclusion that substrate concentration is the dominating variable in the system under study. And just to confirm here or to compare, we got also the COD here as a result of substrate concentration. And you can see like there is really wide or a great variation between COD as a result of varying the substrate concentration compared to almost no change when you change the biomass concentration. So to summarize, the mathematical model developed is good prediction or can predict the performance of the activity/process. It is a simplified system of equations. It has been verified and validated using industrial and lab data. The experimental data were used to fit the model and to calculate the parameters. The model used to study the effect of varying biomass and substrate concentration, and as I mentioned, that the varying substrate concentration led to an optimizing the process condition and improving the effluent stream. But just we need to consider that this results only valid for the system under study under certain design consideration. The model, after all, showed excellent sensitivity to predict the effect of process variable and can be used to optimize and improve the activity/process either during the dynamic step or dynamic stage at the beginning or due to any unpredicted variation of the feed. We have published one article from this work, and it was an amazing experience, and thanks a lot again for giving me this opportunity. Thanks.
Thank you, Dr. Ashraf, for your professor and complex presentation.
And now Dr. Hala, she is working for 18 years in the field of safety, health and environment in the petroleum sector. She has experience in the treating industrial water by physical and biological treatment.
Good evening, ladies and gentlemen. I'm happy to have the chance to show my slides. I'm going to discuss a main problem facing in the petroleum sector when we use a huge water pressurized water to clean the downhole equipment from the petroleum sector, and we use this huge water to clean all the units before maintenance at the workshop. So in my research, I will discuss using agar fiber as a media filter in treating the industrial wastewater out of the washing activity. So the main activity or the main scope of the research is treat and improve the quality of industrial wastewater. To achieve our target in this research, we use 3 steps. The first step, we use oil water separators, and the second, we use trickling system, and the third one, we use agar fiber in our filter media. The advantage was using the treated wastewater in irrigation purposes for non-productive trees, which we needed in the petroleum sector, especially around the lakes in the desert. We can see here from the diagram, this is the figure, the shape of the oil water separator, which is mandatory in all petroleum sector to treat the huge water from all the washing activity in every maintenance yard and in every workshop. And we can find from the figure that the oil water separator is content of 3 stages. The first stage depends on sedimentation, gravity taking. The second one depends on the difference in the density between oil and water. And the third one, it will be at least there is a big removal from sand and mud and oily films. We found from analytic results that the parameter and the characterizations of the wastewater out of the oil water separator we have a big improvement in the parameter. It's compliant with environmental law for discharge, but it still does not meet the requirement to reuse it again in irrigation purpose. So what we achieved beyond the oil-water separator in the first stage, was a good for the first stage, but we need to continue to improve the quality of the wastewater by trickling system. This is a figure showing the trickling system. It contains 4 stages, and we use the outside from the oil-water separator to flow into the different 4 stages. And I can see here we can, in the trickling system, we use the agrofiber. We use different kinds of the agrofiber as a medium. And the advantage for the trickling system here, it was very simple. Apply the process of AMAT, we can put something from different points from each stage easily, far of complexity, and even the operation for the trickling system, it is very easy, and you can move it from place to place. And this is one of the advantages that help the researcher to work on the trickling system without any complexity. Sampling size, you can see the sampling size. First one here, this is the sampling, the N, and the second one from outside from the oil-water separator, and the third sampling point from the first stage, and fourth, and fifth, and sixth, and the eighth, and so on. So this is the size of the sampling to monitoring the quality of the wastewater. So according to the main parameters we are looking to have improve it according to the law, and especially in the petroleum sector, all the side or the rates looking to have improved parameters, especially at COD and BOD and on and grease. So this is the main 4 parameters for industrial wastewater, especially in the petroleum sector. So you can find here that COD have been dropped from 1,500 from 800. So we have more than 44 removal percentage. For BOD, we have more than 50%. For total solid dissolvent, we have 46% removal. And for the last thing, we have in oil and grease, we can find more than 47. So we have more than 67. All the removal and the improvement in the treatment, it was a good achievement for the first stage, but for the second stage and for our purpose, it was not enough, but we need to achieve more improvement less than according to the law 90. We can find here the difference between the result of the first stage and what we need to achieve by the law in the last column. The diagram shows excellent removal for the oil and grease, especially for oil and grease. It was reached 5, which is very, very excellent to encourage us to use what we are working on and to use the trickling system, and especially for alcohol fiber. We reach here to the 5, which is excellent. And for COD, the requirement by law should be 300, and we reach less than 200, which is very good for the alcohol fiber. And the different kinds of alcohol fiber you can see here, besides the diagram, This is all the type of the agrofiber we use it. And what we found for the POD, also we reached to less than 300, which require bicycle. The difference, the gap which is happening between the reality to catch us also to see the relation between DOD and DO, dissolved oxygen, and which is very good. When the DOD is high, meaning oxygen we have it low. There is a reverse relation between both of them, which gives us final result that the result of POD, which is very important and concerned for the people working in the trial system to be low. Here is a different kind of agrofiber we use it from the nature, which is very cheap and available. And this is what encourage us, because this is when the final will help to reduce the cost of the treatment. So we have rice straw, sugar cans, mufa, and hair, and finally we have product. The different kinds have been experimented several times by several weeks of the filter and retention time until we get the best result for our analysis. The treated wastewater after the treatment,
You have 3 minutes.
okay, I don't get it. The treated wastewater have been used in irrigation of the seeds, and you can find from the last, from the first 3 figures, there is a row for irrigations for the seeds. The last one, it was the wastewater before the treatment. Environmental sustainability, and what is the advantage of our research? We have a several advantage. It is help to prevent wastewater, prevent air pollution, prevent soil pollution, and prevent last, it serves the environmental sustainability. All these points help the investor who is looking to work in oil wastewater project to help to encourage him, because he's looking to low cost, easy maintenance, easy operating system, which is needed in meantime to help in the wastewater projects. Thank you very much.
Thank you, Dr. Helen. We can have one question. Yeah. Dr. Helen, there is one question.
Asking about the sustainability of the natural product which you are using. How can we
How we can recycle
recycle
after
the
recycling after
natural product which used as a filter?
yes after using, huh?
Yes.
What?
For the online producing.
Yeah. See, using the agrofiber formulation is an excellent idea. It is very cost, cheap, available as I told you before. We use it as a first as a filter, and after saturating this filter, we use it again. We can recycle it again, or we use it again quite often, especially the factory. Yeah, especially the factory who will use it as a fuel after drying. So this is a good example. And I discussed this item last week with people from EE, environmental team. It was good, especially for rice row, which will help also, to reduce the phenomena of the cloud, black cloud. So this was good because we use all the waste, especially from agriculture. Farmers will reduce it and minimize the waste will be higher, which can be harm to the nature and the human right.
Thank you, Dr. Helen, and thank you for all participants. And I hope that all the attendees have the side discussions and get many questions between them because we don't have time. Finally, unfortunately, the time is going and the time stop which was given for the closing and recommendation is gone away. So Professor Sha'ban and the president of the conference have decided to not to have discussion as there's no time for you not to be more tired. Finally, I want to thank you all, the physical attendance and the online attendance, which we all appreciate. And I would like to thank all the presenters for their nice talks, for the keynote speakers, for the invited speakers. We really get interested for their impressive talks. And so finally, I want to welcome you all to be with us next year in the third International Conference for Membrane Technology and its Application in 2022. Thank you. Yeah, the certificates for the attendance and for the speakers, for the keynote speakers, will be sent to all of you online by email. Also, the recorded talks, and if you have any soft matter for the presentations, you can send us a request via membrane